So last time what we did is we looked at calculating the slope and the intercept of the simple linear regression manually using the building data set. What we didn't do, however, was we didn't find the value of the objective function that we were minimizing. So if you back a couple slides, it was this thing here is what we're minimizing. It's the actual minus the forecasted, or the predicted line, that best fit line, y hat. For each data point, square it, add it all up. All right, so let's see if we can do that for the problem and do it manually. We'll have to do it manually because we haven't done anything else yet. So to do this, I'm going to go back. Remember, this was our slope, this was our intercept. So to get a prediction or an estimate for each one, we're going to call this y hat. And y hat, we use the equation b sub 0 plus b sub 1 times x. Right? So it's going to be b sub 0, I'm going to anchor that, plus b sub 1, anchor that, times our x, which is over in column B. So my prediction for a building that is 54 stories, is 686 feet. In reality, this one was 770. Right, so we under-forecast or underestimated what it was. Now, because I anchored those, I should be able to drag it all the way down. So here it was 428. We estimated 440, so we overestimated. Here we overestimated. Overestimate, under, over, under. Right? So about half should be above and about half should be below the line. Right? And so that's our estimate, but that's not what we need to do. Right? We need to do y sub I minus the estimate, the predicted, the line, and square it. So we need y sub I minus y hat and square it. So y sub I is the actual, the feet, minus what we predicted, squared. And do all that. And then add them all up. So then what we see when we add up all of the squared error terms, the residuals, we get a value of 12,692.71. So that is the minimum sum of the squared error terms, and that is done by this line. So that is the best line that we can come up with, the smallest number that we can come up with for that. So we did that. Now let's go on and do something even more fun. Another way to get it, we'll use the data analysis regression tool. This is an add-in. The data analysis tool pack is an add-in that we will be using. And so we're going to go do that. Let's go back to the spreadsheet. And let's do under data analysis up in the top. And then pop-up box, we want regression, click OK. Input the Y range, that's the thing we're trying to predict, so height. And then we're also interested in the X range, the number of stories, the independent variable. I have labels, so check that off. I'm going to put it on a new worksheet play because this one's getting kind of messy. And that's all I'm going to do for right now. So when we do that, we get summary output. We get the R squared value that we saw back on the scatter plot, 0.8808. And then down here we have an ANOVA table, analysis of variance table. And then we have down in the very bottom, we're looking at the intercept and the slope coefficient, B1. And those coincide or are consistent with what we have done the other three ways that we've calculated it. So here's a fourth way, probably the easiest, most efficient way of doing that. We'll come back to talk about some of this other stuff in just in a few little bit. So notice also that the SS column in the ANOVA table under residual, which is the same thing as error, has the 12,692.7, which is what we came up with for our minimized objective function. So we can get our objective function right here from the ANOVA table. So again, here are the results. We see here the residual SSE. Excel calls it residual for error term, and the slope and the intercept slope. Right. So the end goal really of doing this is to find and interpret the value of the R squared value. So back here we see the R squared value is 0.8809, right? So 88%, often interpreted as a percentage. Now, in order to get that value, we need some intermediate calculations. All right, so and remember that pretty picture where I drew the squares in a previous video? Well, that's what we're going to be looking at again. So again, that's the SSE. Again, Excel calls it the sum of squares due to residuals instead of errors. And we just calculated it manually for our building data set. And this can be thought of as how well the data points cluster about the line that we drew in, the y-hat line. And we're saying that this is the best line, so it better be somewhat decent. Right? Now, what happens if I don't square the error terms and add them up? You should try that and see what happens. That's something very interesting. It'll also tell you why we're squaring the error terms in order to come up with an interesting objective function. So SSE is one part of what we're interested in. The next is also the total sums of squares. Here we say if we had to predict the value of the dependent variable, feet, height, and feet for a building, with only the observations of that variable, that means all we didn't have the number of stories for all those other variables, so we just had the year it was built and the height of a bunch of buildings. What would you use? Well, it might make sense to go ahead and just use the average, or y bar, right? The sample mean of the height. So the total sums of squares assumes that you're going to do that, and what you do is you look at how far each observation, y sub I, is away from that mean height, square it, add it all up. So this can be thought of as how well the data points cluster about the y bar line, the mean of all of the heights of the buildings that we have. So I've drawn in a nice orange y bar, and just for two data points, this is building number 5 and building number 6. I just tried to pick one that was above, one that was below. All right, so we noticed that for the 6th building, if we used y bar as our prediction, we would be grossly overestimating what the actual building height was. For the 5th building, it's the opposite. If we used y bar, the orange line, to estimate how high it was, well, we would be underestimating what it was. And so using y bar doesn't take in any additional information. We think the number of stories is relevant to helping us predict or estimate how tall a building is. And here it seems like that's probably true, since we saw that upward linear trend it looked like. And then finally we have SSR, sum of the squares due to the regression. Here we take our predicted value, y hat sub I, and subtract out the mean, y bar, and square it, add them all up. These can be thought of how much the predicted values deviate from y bar. So then when we put it all together, the total sums of squares, I just did it for one so it wouldn't get too complicated. For the 5th, right, was from the dot to the mean line, the orange line. We have the error term right here on top, how far the actual is from the line, and then we have the sums of squares due to the regression, how far the regression line is away from the mean. Right? So total sums of squares is the sums of the squares of error plus the sums of the squares to the regression. So that's what we do. We put it all together. Then our coefficient of determination, which is r squared, the thing we were trying to come up with, is the sum of the squares of the regression divided by the total sums of squares. So if all the deviation that we're seeing is due to the regression, right, the bigger this top number is compared to the SSE, then the bigger R squared is going to be. This is always going to be less than or equal to 1, because SST is the total, and SSR is part of that total. So the closer it is to SST, the closer it is to a 1, which means more variation is explained. So how do I interpret it? It's the amount of variability in the response or outcome, the y variable, that can be explained by the linear relationship between it and the independent or explanatory x variable. We often report it as a percentage, so in our building example, let's try to interpret it. All right, so if we go back to here, we see an R square of 0.8809, so again we interpret that as 88% of the variation in building height can be explained by the number of stories that the building has. That makes a fair amount of sense and somewhat logical, right? So there's 12% that's unexplained. It could maybe that we could add other variables in to make the explanation a little bit better. So that's simple linear regression using the data analysis tool pack and the regression tool to come up with this, and looking at where those calculations are coming from.